All right, I think we're going to go ahead and start moving this forward. Hopefully more people can join us as time goes on. But I just want to say thank you, everybody, so much for making it to this month's Customer Data Science Meetup. I know the circumstances have brought us to the digital alternative, but I'm glad that we can all hop on. I hope that everyone's having a great week. Midweek check-in. Hope everyone's safe, having a good time. I'm really excited to hear from these speakers, and I hope that we can have a lively, not only lecture, but some, questions afterwards. There'll be two speakers tonight. Both will be, about 20 minutes or so. Great conversation starters and things to learn. If you have any questions during it, Zoom has a handy dandy Q&A feature at the bottom right next to the share screen button. Please go ahead and write any questions you have for either Adrian or Rahul. And after their respective talks, we will dedicate some time for them to answer those Q&As and kind of still have that same format that we had previously. And let me know if you have any questions about that. I'd love to give a shout out to Taylor and Carolyn who helped set this up. And again, obviously Adrian and Rahul who were able to come in today to talk to all of us about their respective topics. Without any more, I'd love to introduce Adrian. Adrian is a data scientist and investor. His previous companies was at WAG and Uber in data science and analytics. And here, as you can see on the screen, is going to talk about Fooled by Data Science, how your infant nephew can sometimes forecast better than AI. So please give it up via Zoom for Adrian.
All right, I can tell the crowd must be going wild right now. I hope everyone's doing well. I'm looking forward to getting the show started. And just last thing, Adam, before I start, can you see the slides?
I can see your slides, yes.
Okay, and can you see me as well?
I can.
All right, great. So I'm gonna just dive right in. As Adam mentioned, I'm gonna be talking today about the topic Fooled by Data Science. Basically, I'm a practitioner in the field. I think the toolkit is extremely valuable. I think, if you want to make a huge impact in a tech company in this day and age, like being able to understand analytics and data science is critical in making an impact. But like all things in life, this toolkit does have limitations. And I do think it's important to call out some of those limitations because frankly, in a lot of the circles that I chat with, I find sometimes that folks can get a little too hyped up about the AI and machine learning stuff. And so I'd like to address that in my presentation. One moment. Okay, there we go. Just a little disclaimer. This only represents my thoughts, no employers, clients, peers I work with. And with that, we're going to get started with a very brief lesson in history. So let's ignore coronavirus for a second and let's go back to the 17th century, back when the Dutch were actually the leading global power, utilizing their commerce arm, the Dutch East India Trading Company. At that time, there was a lot of popularity for tulips. They're, I think, primarily grown in the Netherlands, and they are beautiful flowers, but for whatever reason, there a lot of people in the mid 17th century showed an interest in tulips. And basically what ended up happening from this is people noticed that certain groups were bidding up the price of tulips, which signaled to others that they were valuable, which then in turn led them to basically adopt this herd-like mentality of further bidding up the price of tulips. All of this ultimately led to a very spectacular market collapse where I think at its peak, the price of tulips was trading like at the equivalent of almost like buying a house at the time. People were posting, very valuable assets as collateral to get money to trade tulips. And, this market collapse led to the insolvency of a lot of institutions and individuals. And this was kind of an early example of how people can sometimes irrationally behave in herds. Let's fast forward a little bit now, get a little more closer to contemporary times, 1987 specifically. There was a very famous trading day in 1987 that colloquially is known as Black Monday, excuse me. It was the day, ignoring coronavirus, of the single biggest market decline in stock market history. I believe the stock market declined in a single day, I believe 17%, but please don't quote me exactly, but it was a massive, massive steep drop. And basically in the post-mortem, when people tried to better understand what was going on at the time, a lot of investors in that period of time were very pumped up about a technology called portfolio insurance. And basically what this technology did was, it was an algorithm that in your portfolio, if it saw that the stock market was going down, it would automatically sell stock. And a very similar kind of phenomenon to Tulip Mania was going on here, where certain institutions began adopting portfolio insurance, which got other people excited because they wanted to copy institutions, which led to further people wanting to kind of join the herd mentality. And basically on this day in 1987, I think the market opened with one very strong sell order, and that just triggered everyone's algorithms to just sell the market, which led to the crash. I talked a lot about commerce in these first two examples, so I'd like to now fast forward and talk about a technological example here, more specifically the Segway scooter. I'm sure everyone in this talk knows what the Segway scooter is, but in 2001, when they were debuted, you know, there was a lot of hype around this stuff. I mean, people were saying this was going to redefine the way cities were designed, the way we navigated around malls. It was going to basically create a brand new economy around micromobility. And obviously, you know, if you look around pre-corona, walking around the streets, I don't think many of us, at least in LA, are seeing Segway scooters around. And ironically, in a very strange twist of fate, the founder of the inventor of the Segway scooter actually died falling off a cliff while riding a Segway scooter. So here you see another example. You know, I think people started getting hyped up in the crowds. It led to this particular thing getting very hyped up in particular, and ultimately nothing really came to show of it in the end. So now we get to 2020, and basically I'm navigating this moment with a lot of this history in mind, and there's just a lot of traits that I'm starting to see in this AGI community that I believe you can also recognize similar traits in these previous examples that I called here. So what is the trait more explicitly that I notice? We systematically behave in herds, and oftentimes in ways that are irrational. I think, you know, back when we were hunters and gatherers, it actually made a lot of sense to operate in herds. You know, if my tribe member was getting attacked by a lion and I alerted my tribe that there was a lion, it would mitigate the risk of losing life because we all could react quickly to the threat of a lion. However, in the world of interconnectedness and globalization, you know, this herd mentality that we have can oftentimes backfire actually in our decision making. And this behavior is very pronounced in technological advances, and I think I'm starting to see this in the AGI community as well. So I'd like to actually spend the rest of my presentation bringing up two specific examples of where I think we're having some blind spots in the way that we're using this technology to make decisions. And I'm going to just dive straight into the very first one. It's OOD, which stands for out of distribution. Basically, this is a problem in machine learning and artificial intelligence where you have training data and it has a particular distribution. And then when you do your train test and you actually productionalize your model ends up spectacularly failing when it gets an input that was very much outside of the distribution of the training data upon which it's studied. And so I'm going to use the stock market one more time as just another really good example here to convey this point. You can see here on this slide, I graphed the distribution of annualized returns of the S&P 500 index, which is a commonly traded US financial index. So these are returns, the annualized returns since 1928. And you can see roughly, there appears to be a somewhat of a right skew, but relatively normal distribution here. And yeah, you know, there's a couple periods of time. Let's see if I can get the pointer action going. Yeah, you know, you had a couple periods where there was really good returns, you know, 40% plus returns. And then conversely, you had a couple pretty bad years too. And more specifically, in the 93 years of data that I looked at, there were only 6 cases where you had 20% losses or more in a given year. Now, I think a very common workflow I've seen both in the analytics community and the data science community is they look at a particular distribution, they say, you know what, these outliers probably aren't that important, so we're going to ignore them. And I think in cases like the stock market and a few other examples that I'll mention, this can really, really hurt you. And we can see that here in the next slide. I ran a simulation where I basically took a $100 investment and I let it for this 8-year period experience for most of the period of time, the average returns that you saw in the previous slide here, with only 1 year of a really bad, what you can maybe consider like a black swan event. You know, the market goes down 30%. And I think when you look at this visual, it really paints the picture of how important these outliers are. You know, if you ignore the outlier here and we look at our returns going from year 1 to year 7, we actually our total return at this point is roughly 50%. So we did insanely well. But with this only one bad year where the market goes down 30%, our investment has only made 5% in an 8-year period, which is not that compelling of a return profile. And so why do I share this slide? The point here basically is the outliers in these examples are oftentimes some of the most important data points that you actually need to study in your data set. So rather than ignoring them, it can oftentimes be in your best interest to try and better understand what's causing them and also trying to model them in your data as well, in your modeling, excuse me. You know, look, I've been talking a lot about like trading and stocks in this presentation. So I do think there's some other non-trading examples of where the outliers can be really critical and ignoring them can lead to very bad model production. You know, I think another example is if you were to build some sort of model around predicting the amount of annual visitors on a website, where, you know, you have Amazon, Facebook, Instagram, Twitter, you know, these websites are generating the overwhelming majority of traffic online. But, you know, besides this very small group that are also would probably look like outliers in your data set, most of everything else is pretty low. And in that case, you have another instance where actually all of the meaningful data is in the outliers as well. And one more example that may be a little more relevant to our moment that we're experiencing now, I would argue, is if you were to study the distribution of Lysol by household during COVID-19. You know, I think we've all been reading reports now of a select group of people systematically hoarding Lysol and cleaning-like products. So I wouldn't be surprised if you were to study the distribution of these products by household, you probably see a couple that have just insane stores of these cleaning products, while the overwhelming majority of the country lacks these. And I think that's another great example where, again, like the outliers actually tell you a lot, and ignoring them can lead to serious flaws in your modeling. Look, there is definitely workarounds to dealing with out of distribution inputs in production, in a production model. I actually cite a paper here that goes into one workaround. This paper was actually led by this gentleman. I'm going to butcher this name, but Mr. Lakshminarayanan, more specifically. Let's see. Oh, hold up. I think I'm still on. Wait, Adam, can you see the slide still, by the way? Can you see the...
I can see the PDF of Can You Trust Models Uncertainty?
Okay, awesome, thank you. So basically, look, I include the link on this presentation. I'm sure it'll be shared with all the attendees after. But basically, in this paper, they go into the idea of ensembling, which I'm sure many of you are aware of, which is basically the practice of taking a lot of pieces from various different models and combining those in aggregate to produce something that has a higher accuracy than just using one model alone. So we talked about out of distribution as being one blind spot, I think, that exists in a lot of the modeling that is going on in our world today. And another super important one that I would like to call out is bias in randomized data. I think there is for whatever reason in the community, there's a sizable group of people that believe that if you just do your train test split, you know, in the sklearn package, doing, you know, your train test split, you know, it's like literally one line of code in Python, that you're basically randomizing your data and basically eliminating a lot of the bias in the way you model. But that alone is definitely not enough. And I think this visual kind of paints the picture pretty clearly to start. I think maybe a lot of folks here have worked with the ImageNet data set. And for those that haven't, it's a very popular image classification data set that's used in neural network and image classification models. And you can see here of the 14 million labeled images, almost half of them actually are pictures of people that are based in the United States. And so what does this mean? You know, if you were to just do some very simple sampling of this data and then run your model on it, the model will probably do a very good job of doing identification for people in the United States specifically, but may have very severe deficiencies for people trying to identify key attributes of folks in other countries. Look, I think this is a pretty innocent and harmless example, but there can be very, very real world implications of not fully randomizing your data to eliminate bias. And I note a quick passage here. I'm quoting a study that basically these folks tried to build a system to detect the level of risk of prisoners. And basically what they ended up finding was there was a disproportionate amount of non-white prisoners that had their their risk level raised by the model relative to the relative to the white prisoners. And look, I don't really know in detail how the data scientist team here prepared the data and did their train test splits and all of this stuff. But I certainly know, as just an American citizen, there's certainly an incarceration problem in the US where there is a disproportionate amount of non-white people in prison. And so if you're not controlling for that data in some way in your modeling, you're going to produce an output that does this sort of work. Essentially, if you don't try and eliminate the bias from the real world when you try and take it into the world of machine learning and AI, you're going to only just bring that bias with you. And look, I do want to, I am a practitioner and I don't like just talking about, high level concepts. I do think discussing workarounds is critical here. So look, there's two big workarounds definitely to address this. I think one of them, it is taught, I think, in a lot of these Udemy courses now. It's basically the concept of downsampling or upsampling. So basically, if you are studying a prison data set and you have a disproportionate amount of non-white prisoners in the data set, what you can do is you basically can randomly select a certain amount of non-white prisoners such that your training data set has an equal proportion of white and non-white prisoners. So you're at least trying to eliminate that bias a little more. And you can do the opposite too, where you can also increase the amount of underrepresented folks to try and create that balance too. Another workaround, this is actually from high school AP statistics. So shout out to my AP stats teacher there. But this actually does work pretty well too, stratified random sampling. Basically in your exploratory data analysis, when you're kind of playing around with your data and running a couple of different graphs to better understand key trends, if there are certain key cohorts that you recognize as being very critical in understanding the underlying data, you can make the decision before you begin the modeling of deciding to essentially pick out an equal proportion of folks from all the different key cohorts that you identify from your exploratory analysis. And in this way, you can also mitigate the impact of the bias in the modeling. I do want to call one last thing too. There are other examples of bias in randomized data that I think is very important to call out here. Brett Weinstein, who was I believe, a professor at Evergreen University of Biology, he released some research that found that the laboratory mice that were being used in all of the clinical trial testings and a lot of the testings where you read about laboratory mice being used in experiments, he found that all of them were coming from the same facility, and all of them tended to have much longer telomeres than mice in the wild. Telomeres is basically a part of the chromosome, but what does this mean basically? The mice that they use in all the studies for the prescription medicine and the generic medicine we all take didn't actually reflect how animals in the real world may have reacted to the medicine. And so I think if we all lived in captivity, it probably would still be very applicable, a lot of the research done with laboratory mice, but obviously, outside of COVID times, we are not animals in captivity, and therefore the laboratory mice may not be a good data set to use in analyzing kind of clinical trials. There are some additional blind spots I have noticed in this field as well, but I only have so much time to present. And yeah, if you're interested in learning more, please reach out to me. And I'd like to thank you all very much. And I'd love to take any questions, comments, or concerns either now or after Rahul presents.
Awesome. Thank you so much, Adrian, for that.
Should I stop sharing, by the way? Like, what do you?
How about you just leave it on this thank you slide, and I think there's a question for you. Maybe Carolyn can help me navigate the this Q&A and chat bar that we have open. I see.
Absolutely. So if anyone has a question, you can click on the little Q&A button at the bottom, and that will pop up a box where you can submit a question. So we have one question that came in. What's an example of herding? And AGI is reading the same paper on Arvix, an example of it.
Wait, is there a way that I can also see the questions in writing, by the way? Because
yeah, so this one came in through the chat.
Oh, cool. Here, I'll just pull it up one sec. It's an example of herding. Yeah, so basically, no, good question, Dan. The basic kind of high level idea I'm seeing here is, similar to with the portfolio insurance, there was a select group of, people in ivory towers that were using this one product, and other people kind of noticed them using it and wanted to copy them. I'm just seeing a similar psychological phenomenon going on in the artificial general intelligence space, where there's a select group of people that are learning to use these tools and are beginning to apply them. OpenAI, I think, is a great example of a company that's doing a lot of work here. But I think there's now a lot of hype in this space where people now think that AI and machine learning can be used to solve every single problem you can imagine. And so when I talk about the herding, I think it's this phenomenon, Dan. Basically that everyone is just now convinced that AIs can do everything, when in reality, as I tried to show in this presentation, there are real limitations.
I actually have a question for you, Adrian. Kind of building off that last one, that timeline you showed was really interesting, of tying, the explosion in tulips to the Black Monday to the segues. Do you also think that there's a crash of AGI coming, as in like there's a huge hype cycle that may be so large that it squashes a lot of the research efforts going on, or is it more we're going to hit a wall that we can't push through as a technological upgrades come in?
Sure. I think you're actually already seeing, like, I don't know if there's going to be, one big crash where just everything burns and all of this, but what you're certainly seeing is the hype, kind of some downside impacts of this. I can think of two examples off the top of my head. One of them is, I'm sure some of you read about the launch of the Apple credit card, the digital credit card, in conjunction with Goldman Sachs. Basically, Steve Wozniak and a couple other folks started complaining after the launch that it appeared that the automated application process was unfairly and systematically biased against women. And look, I don't have access to the data set. But another example I can think of off the top of my head is basically, a lot of these cities are trying to use facial recognition technology. I think Seattle at one point was flirting with it. And I think, there's been a number of instances where people have been incorrectly identified. And basically, like, look, I don't know if there's gonna be one particular crash, but you certainly see these types of instances of just examples of where, like, the application of technology can, like, fail, like, miserably and lead to really negative outcomes that the user did not intend.
Thank you.
Oh, by the way, there's a webinar chat question here. What's the story of your nephew that you mentioned in your topic? That was more to just be kind of like teasing a little, just like, like, because AI can have some limitations, sometimes someone with a very rudimentary understanding of the world can actually predict better than AI can. And that's all I meant there. Yeah, it's supposed to be like a playful thing.
Adrian, you have a couple questions in the Q&A chat. One from Doug, one from Joffrey, and one from Dan. I think the first one you just answered.
Okay.
I'm gonna I'm gonna miss it.
Okay. Okay, so let me just answer Doug's. In a small imbalanced data set, will you upsample or downsample? Okay, well, interesting question. I mean, look, I think if you have a small data set first, like, we know that it's very hard to generate statistical significance when studying small data sets, unless you see an insane level of metric uplift in the core kind of metric you're trying to predict or optimize around. And so basically there, it's I think a lot of what I presented here is working in the world where you are using larger data sets, because you can build some, you can use machine learning models and AI on smaller data sets, but the applications of that don't have as much of a dramatic impact as the applications of this technology being used with the large data sets. By the way, Adam, do you mind if I kind of just like drill through these? Because I see there's a
No, go ahead. How about we cap it at these four that are posted, and then
Sure.
we'll move on from the Q&A.
Sure. The problem number 2 seems like it is part of a broader problem where data scientists are not aware of the selection biases related to what data is included in our data set. But sometimes we just can't know all of that, especially if we didn't collect that data. Are there mitigation techniques you'd recommend in those cases? It's an interesting question. Look, I think if there's one thing that I've learned in my experience in this world doing analytics and data science, like there seems to always just be 2 hats that you have to wear. There's the hat of kind of like the the technical person that is learning, if you're learning Python or R to be able to build the model and play around in a Jupyter notebook. But there's also just the role that you need, that I've seen good data scientists do, of just being really intuitive kind of business stakeholders, where you don't just only know the technology, but you also understand kind of like who your customers are, like what is going on in the data set, like where are some kind of hidden risks. And so, look, I can tell you, if you ever have to build these types of models in a corporate environment, I think the best way to mitigate the risk, and something that I actually rarely see data scientists do, is literally just take an afternoon and go sit with the salespeople, like hop on some calls, like if you're in some sort of sales business where you're trying to generate customers, and talk to the people that actually speak to your customers. Because in that example, you for sure can capture things that may not necessarily be easily found in your data for a matter of reasons. And so I think that is one way to potentially work around it. I'm going to continue. The US GDP in 2020 Q2 is down 4.8%, but the S&P 500 is back up. Is this hurting or just the Fed's actions? Look,
And,
I'm not.
and Dan offered a correction later down in the Q&A. But we'll just see. I mean, he meant to say Q1.
Sure. Look, I'm not going to comment on. I actually told Taylor, Adam, and Carolyn before this call. There's a line that I always tell people, that if they want to start playing around the markets, the market can stay irrational longer than you can stay solvent. And so I think anyone in the business of trying to really predict or understand what's causing a daily or even a weekly stock move, like it seems to be in the long run a losing game. So I try not to play this stuff. But Dan, feel free to shoot me a tweet or an email. I'll leave my info here and we can chat offline. By the way, Adam, I have 1 or 2 more questions?
Yeah, these last 2 questions,
okay.
I think would be great.
Awesome. Do you think the current COVID-19 situation will just be an outlier, or will fundamentally shift the basis of all data sets, analytics, making historical data not useful? It's a really interesting question. Look, my view of the world is very much grounded in a similar view of the world that Nassim Taleb shares. So, one of my personal favorite books is The Black Swan, and if you all haven't read it, I highly recommend it. And the basic gist is, the reason why humans are really bad at predicting the future is because there's a very small amount of events that have an outsized impact that tend to drive our kind of future. So whether it's a pandemic, or whether it's a war or a famine or a drought, it's less, think about what I was talking about earlier with like the distribution of Lysol products owned by household. You can almost think about it in this way, where it's like, the average person on a data set doesn't really mean much, but it's those few people that are hoarding all of the Lysol products that actually are what you want to study. And so similarly, it's these types of events that really drive the course of history. And so rather than saying historical data is not useful, I don't think that's what the issue is here. I think what we need to do a better job of is recognizing that we don't know a lot more than we do know, and kind of embrace that uncertainty in the way that we do our modeling. And Salvador, I'm happy to go into more depth there, but I do have a time limitation. So feel free to reach out to me on Twitter or LinkedIn, and we can go after it. I think this is my last question. How will you add the COVID effect into a sales model, for example? I mean, it's Shayla, thank you for the question. I think the premise is a little broad. What are we selling? I mean, if we're selling medical equipment versus selling, subscriptions to, or selling like theme park tickets to Disneyland, I think kind of the way you treat the data there will differ very significantly. And so look, like, I don't think just with what you shared just there, I don't think there's a ton of depth I can go into, but again, shoot me a tweet, shoot me a LinkedIn message, even shoot me an email. And if you can maybe provide a little more context, I think I can do a better job here of answering the question. And I think that's it with my time. I want to thank you all so much. Adam, Taylor, Carolyn, and the Retina team, thank you so much for letting me speak. And yeah, I'm excited to hear Rahul speak too.
Awesome. Thank you so much, Adrian. This was a really great talk, and I really loved the idea of making sure that as data scientists, we really focus that there are biases in any problem we have, especially things that fall outside the distribution that can completely change the outcome of our model. And we need to not only be cognizant of that, but actively work to mitigating the risks that those biases and those outliers can have. So thank you so much for presenting. So yeah, thank you again, Adrian. Thank you everyone for your questions. Please reach out to Adrian if you have any more questions. I'm sure he'd be glad to answer them. But next up, obviously, we have a second speaker on our bill today. Rahul is a senior data scientist at Neustar for 5 years, and he will be speaking on the intersection of machine learning and Spark. So please give it up for Rahul.
Sorry, I was muted. Thank you. Hey, my name is Rahul Vaswani, and today I'm going to talk about classical time series forecasting with Spark. And so, let me just get this pointer going. So what are we actually going to talk about? It's what is classical time series forecasting, basically using ARIMA and SARIMA. What's available for me to use in Spark right now, and how can we utilize something called the Pandas UDF to help make forecasting in Spark simpler? So first, what is classical time series forecasting? Time series are basically anything that is observed sequentially over time. And time series forecasting then is predicting future values of a data based off its history. A couple things that we have to have is historical numerical information, and we assume that past patterns will continue to the future. Obviously, in the time that we're living in, that's a little bit suspect, but we can talk about that stuff offline. And so here we have previous observations leading to a new observation in the sequence. Before we go on, I want to talk about a couple of terms or terminologies in time series. This is pretty much for people who aren't very familiar with time series forecasting in general, so please bear with me here. First is autocorrelation, and autocorrelation basically measures the correlational relationship between lagged values of a time series. And so here we have an autocorrelation graph, and this is pretty much the relationship between the original time series and its corresponding lag. So this x-axis are lags of the data, and the blue outlines here represent whether correlations are statistically different than 0. And the x, so once again, the x-axis represents the number of lags, and the y-axis is bounded from -1 to 1. And we have down here a partial autocorrelation graph, and partial autocorrelation is pretty much correlation that results after removing the effect of any correlations due to terms at shorter lags. And so why this is important is when you're actually doing time series analysis by hand, or just statistically sound analysis, the autocorrelation function and partial autocorrelation functions will actually help you get your arguments for your time series model. The second term that I want to go over is stationarity. And basically stationarity, it can just be defined by this. A stationary time series is one whose statistical properties such as mean, variance, autocorrelation, etc., are all constant over time. And most classical time series models require that a time series is stationary in order to generate reasonable forecasts. And so I have this quote down here: if a time series exhibits stationarity, we're able to detect changes in a predictable way. And here is a visualization of a stationary time series. So we know what stationarity is now, but how do we achieve a stationary time series? This visual is taken by Forecasting Principles and Practice, a book by Heinemann. And basically we see here, we have our original time series. Then we see that the variance is fluctuating over time. So what he did here is he took the log to kind of get the variance to be static. Then he seasonally differenced the logged equation, and he has a somewhat stationary time series, and then he did a double difference again to get a more stationary time series. So here we see we have to do a couple transformations to get to a stationary time series. And so ultimately what we care about is how to model time series, right? And so there's a few steps that I recommend going through in practice of modeling time series by hand. First is we plot the data and we notice if there's any unusual observations. Here we see that the variance of our time series is decreasing over time. And so if the variance fluctuates, we'll apply a logarithm or box-box transformation to the data. And so here I applied a logarithm to the data, and we see while this data does look kind of similar, the scale is very the scale is very like granular. I've reduced the variance by instead of these large amounts. So once we have kind of like a stable variance time series, we then difference the data until it looks stationary. We might need seasonal differencing. And here, once again, if you're doing this by hand, you can kind of eyeball, create visualizations and then eyeball whether or not time series is stationary. And then there's also the KPSS test that we could check for stationarity of the time series. So once we kind of difference our time series and look for whether or not something looks stationary, we could plot the ACF and PACF, the autocorrelation, partial autocorrelation graphs, to determine the corresponding autoregressive and moving average terms. And so here we see we have a graph. We can see that after like lag 1, everything is insignificant. So we might want to deal with something with an AR term of 1. Then what we could do is run a model, and in true computational machine learning fashion, we'll keep iterating until we get a low AIC, which is basically an accuracy score for the model. And to be sound statisticians, what we'll do is we'll check to see if we'll check the residuals to see if it resembles white noise. And a time series is white noise if the variables are independent and are basically IID with a mean of 0, and it shows no autocorrelation, which is kind of what we see here. So with that kind of terminology out of the way, I want to introduce the SARIMA model. And so SARIMA stands for Seasonal Autoregressive Integrated Moving Average. And it's a model that aims to describe autocorrelations in data and ultimately forecast that data out. So here we see we have the original data, and then we have our little blip of a forecast. And then I have some math here. I'm not going to go into the math, but if you want to talk further about the math, we can talk about that offline. But just note here, we have AR of a P term, we have D, which is differences, and our moving average terms is Q. So when we kind of code this up, we think of this SARIMA equation, which is, once again, P, which is the order of autoregression, D, the degree of differencing, Q, the order of the moving average, and M, which is the frequency of the time series. A lot of these parameters, like I said earlier, can be inferred from the PACF and ACF graphs, but in general, what we have are these lowercase and uppercase letters, lowercase for non-seasonal components and uppercase for seasonal components. And so we care about how to code this up. R has the easiest, has basically the easiest to use and most comprehensive library forecast, which is written by Heinemann, which has an auto-arima following, which allows the computer to easily pick out the necessary PDs and Qs based off the data provided. Neil Foltz actually did a talk, I think, a couple months ago at this meetup about using auto-arima with R. Python has a SARIMAX function in the stats model library, which would require looping through ranges for P's, Z's, and Q's in order to find optimal values. And Facebook also has a forecasting package called Profit, which works in both R and Python. And I think it adds some Bayesian terms into that. And I know it's becoming very popular right now. So we got the time series kind of concepts out of the way, but now let's talk about time series forecasting in Spark. So first, why Spark, right? And before we get into that, what is Spark? So Spark is a lightning-fast unified analytics engine for big data and machine learning. It works with a file system to distribute your data across a cluster and process that data in parallel. So for large amounts of data, it processes it fairly quick. Spark allows for fast data processing, easy to use APIs to process that data, and allows for unified data engineering and data scientists to come together. And one of the best parts about it is you can utilize Spark in a variety of languages: Java, Scala, SQL, Python, and R. And if this seems like a pitch, it kind of is because I got it from the Databricks website. But there we go. So what is currently available in Spark? So what was built specifically for Spark? There's this time series package called Spark TS. It's a Scala, Java, and Python library for interacting with time series on Spark. The only problem with this, or let me preface with one problem with this, is it's no longer under active development. And so this library isn't currently being maintained. But it is a great package with decent documentation in Scala. However, the PySpark documentation is a bit lacking. So according to the documentation, it requires you to first create a time series RDD. And this is kind of similar to in R where you need to create a time series object to forecast. And it supports ARIMA. However, it does not support the seasonal component of ARIMA. And there are workarounds such as, applying a pipeline of transformations to detrend, remove seasonal components, et cetera. But you still have to do those workarounds to get this to work. So I'm going to show some code, but before I do that, let's take a look at the data. So here we have the data that I'm currently using. It's basically aggregated marketing data. It's monthly, where this value is price in US dollars. And I obviously didn't trim those decimals, but it's price in US dollars. And so what is that data? What does this data look like? Here we have basically the data. We see that the variance is fluctuating. It doesn't look like it's trending downward, but not significantly, or visually not significantly trending downward. So let's talk about Spark TS ARIMA. And so rather than going through those steps that I explained in the modeling process, Spark TS ARIMA actually has an autofit function. And so first we need to create our time series object, which is what I do up here. And then we have our RDD. And after we have our RDD, it's as simple as calling arima.autofit. And we can see what the P's, D's, and Q's it chose was. It chose 001. So this is basically an MA1 model. And here we see the original values and then what our model fit to those values. So like I said earlier, it settled on a moving average of order 1. And it's honestly not bad given the lack of addressing seasonality. And Spark TS ARIMA is easy to use once you figure out how to do all those time series RDD configurations. So figuring this out actually took a little bit of time because the documentation was lacking. And fun fact, despite what the actual docs say, you don't need a time series RDD. You just need a NumPy array. So that was fun after doing all this. I figured out that, hey, we could just plug in a NumPy array here and it works pretty well. So now let's talk about time series forecasting using Pandas UDFs. Before we do that, why I'm talking about this new topic is a lot of firms and a lot of people already have pre-built Python models for forecasting time series. And a lot of it is built off regular packages, particularly the stats models package. So I'm going to explain a little bit more about that as we go on. But first, Pandas UDF is basically known as a vectorized UDF. It's a user-defined function that uses Apache Arrow to transfer data, and then Pandas to work with the data. You basically define a Pandas UDF with the keyword Pandas UDF as a decorator to wrap the function, and no additional configurations required. There are a bunch of Pandas UDF types available, but for time series forecasting, and for this example, we're going to be using the group map type. And if all this seems really kind of too in detail, we could just say Pandas UDF is a decorator that can be used to wrap functions using Pandas syntax in order to run common data science libraries in a parallelized manner. So as I stated earlier, I'm going to be using stats models. Stats models has a streammax function which can be used to estimate seasonal ARIMA. There is no autofit-like function here, so we're going to have to loop through P's, D's, and Q's in order to find the best model that fits the data. We can use AIC as a benchmark, but in the example going forward, I'll be using MAPE, which is mean absolute percentage error. And a lot of firms already have this. If they're Python-based, they already have streammax models in place. And so what does it look like if we're not using Spark? We basically have our Pandas data frame with our sorting values for date, and we're setting our index as date. We're looping through our P's, D's, and Q's for what we think would make the most sense within our ranges. This NCT-CT is basically trying to figure out what the trend looks like. And then here we have our MAPE, which we're setting to infinity, our AIC, which we're setting to infinity, and then we're looping through and seeing which model gives us the lowest MAPE. And we're using kind of like a recency weighting. So as long as the recent data fits pretty well, that's the model that we care about. That's the MAPE that we care about. So what does that look like? The best order that we got, we have 202 So 202 non-seasonal component, and then 100 seasonal component. And here we see that unlike the Spark TS package or the autofit function, here the fit looks pretty decent, especially for the most recent data. And so we're satisfied with this. Now, that was a non-Spark processing. So how do we actually take that code and plug it in to Pandas UDF so that we can use Spark? And as we stated in a previous slide, all we need to do is wrap our forecasting code in a function and add a decorator. So here I have the Surima function. I have a decorator up here, and then I'm pretty much good to go. All I have to do is call my data frame, group by metric, which in this case, there's only one metric. So it's just grouping by one thing, and then it's applying Surima. And the forecasting results is the same as we saw in the stats models, forecast the fit, and here's what our forecast looks like, this little blip, which is in line with kind of what we expected to see. And so you might be asking, does Pandas UDF really make a difference? And so honestly, it's slightly slower if you're only forecasting one series. However, if you're trying to model multiple time series, Pandas UDF really outshines using non-Spark Surima forecasting. And to show that, I'm going to examine the time difference between using non-Spark and then Pandas UDF forecasting. So here's a series that we're going to forecast. Think about it like panel data, where each one of these is a specific dimension within that data, and then we have our time series here. So if we take CHLD CL1, we have data from 2015 to 2019, and each one of these has the same similar kind of data there. And so if I have a non-Spark Pandas code, basically the same thing I showed earlier, and the command took, you can see on the bottom, the command took 19.14 minutes, which was quite a long time to run. However, if I wrap that into Pandas UDF and ran it, the command took 5 minutes. So it's almost 200% faster just wrapping it in a Pandas UDF. And the code is literally almost the same thing. Yeah, we basically just took this Surima function, we wrapped this into a function, and then we put that decorator on top, Pandas UDF. So quickly to recap kind of what we went over. We went over what is classical time series forecasting and a couple of key terms to know. Autocorrelation, which is a correlation between the lag values of the time series. Stationarity, which means you have constant mean, variance, and other statistics over time. And it's necessary to have stationarity in order to forecast. And Surima, which is a seasonal autoregressive integrated moving average model. We also went over what's kind of available for me right now in Spark, like just general Spark package to use. And that is, it's a third-party package by some guy from Cloudera, but it's built for Spark. And it's called Spark TS. It has great docs in Scala, not so much in Python. It doesn't support seasonal components, and there's going to be very little to no support going forward, just because the creator doesn't have that much time to work on it. And then we talked about, okay, if Spark TS doesn't give you what you need, how can we use a Pandas UDF to make forecasting in Spark simpler? We can do AutoRima via loops in regular Python, but it's slow. And Pandas UDF allows us to allows us to parallelize the code via Pandas syntax. So a couple of quick kind of closing words that I had was Databricks has a great article on time series forecasting using Pandas UDF and Profit, which is really good. Like in case your firm currently uses Profit and you want to parallelize that with Spark, this article has a great example of how to do that. I borrowed extensively from Heinemann and Athanasopoulos. I highly recommend their book if you're interested in getting into time series forecasting. It's free online, like they just gave it out for free, which is awesome. I forgot to mention this earlier, but the folks at 2 Sigma have another package made for Spark, developed specifically for Spark, called Flint, which is a time series package. However, from when I checked, it didn't have any forecasting capabilities. And I also mentioned this earlier, but Neil Foltz gave a great time series talk at a previous CDS meetup. And I think there's archives to watch these presentations. I highly recommend that. That was a really good presentation. So quick thanks to a couple people that helped here. Anna Dorfanko, Yifei Wang, Girish Govindarao, Girish Chandri, and Israel Alanese, and then my team at Neustar. And the last thing before questions is, I know that times are tough, and I know a lot of people have been displaced from their jobs and are looking for new opportunities. I'm going to try and help out any way I can. So if you see an open position at Neustar that like you're interested in, please reach out to me. Or like if we're connected on LinkedIn and you see that you want to be connected with someone that I have a connection with, reach out. I'll do my best to give an introduction or something like that. So that's out. Thank you.
Awesome. Thank you so much, Rahul. This is really informative and very cool to see the impact of Pandas UDF on the exact same code, which is great. We have a couple questions in Q&A. Let me know if you can see them. And everyone watching, please feel free to write in and have Rahul answer your questions live.
So the first question by Jason, why are we using Spark? Is it because of the package in Spark? Yeah, so like basically for our firm, a lot of the data processing and modeling that we do is built on Spark. And so in order to have that same kind of seamless process, we just wanted to see what forecasting was available with Spark. And then we found that lacking. And we thought of a good way to use existing non-Spark forecasting and parallelize it. So that's why this is mainly for Spark. And then what is a good predictive models in terms of accuracy, and what model to use when the data shows a combination of seasonality and no particular pattern? That's a good question. It honestly depends on what you're looking. So in terms of accuracy, like you could go for just any kind of regression model. It doesn't necessarily have to be time series, because if you think about it, like all time series is a sequence. So you go from 1 to n. And so if you have any regression model and you kind of want to push that out to like whatever, like n+1 to n+p, you can use kind of any regression model and whatever seems to work. One of my buddies used XGBoost to make a regression model and it looked pretty good. So yeah, that should help. There's also other covariates that you can kind of put in to work, but this was particularly for univariate time series analysis. Khan asks, so you have a data set and you have a lot of features, and time is one of them. The question you're trying to answer doesn't concern timing, but rather a quantity. Would you go with a regression solution or still go with time series forecasting? So I would go with the regression if you have information about those other covariates in kind of like a future setting, right? So if you don't have other information, or if you can't intelligently kind of carry over that other information, then you would want to look at multivariate time series models. You could use like vector autoregression, and there's a couple, like even they have a linear model using like time series to help with the error term. That might help, or like linear model with like ARIMA helping with the error term, that might help. But if you're just interested in the quantity, a regression would work just as well. There's no need to kind of forecast data out using like a classical time series package if you can just do regression. Thoughts on doing this with SparkR or SparklyR? You can. I'm not like, I personally don't use R that much, but I'm pretty sure Databricks has articles to like how you can wrap not like R functions with maybe just even using a Pandas UDF or something similar like that to forecast and to parallelize. And in fact, if that works and you could use Heinemann's forecast package, then you'll probably come up with a better model than I would. But yeah, so if I'm not familiar with how to use SparkR or SparklyR, but I'm sure like Databricks has articles that can definitely help out with that. How efficient and stable is it to pass data between Python and JVM in a Spark cluster? That's a good question. And I actually asked that question to one of our senior data engineers a while ago because I think Dask was blowing up, and I was curious about like one of the selling points for Dask was it's not using that JVM. And I think his answer was it's like the PySpark API has gotten a lot better, where it's pretty stable and efficient to use it now. It might not have been in the past, but it's pretty stable and efficient to use it now. But if you send that question to me and follow up, I can actually email you with him CC'd, and he can explain it better. He's solid.
So we probably have time for one more if one pops up, but if nothing comes up in the next couple of minutes, we're good to go. Well, we've got two right when I said that.
Oh, yeah. Did I compare the results for Arima Surima for my particular data set with other models? No, I didn't. Only because basically the business owner wanted to see for when we were running this was the outputs of an Arima Surima model, just for explainability. Because once again, with those autocorrelation terms, we can explain it a little bit better. But yeah, this was basically, the whole point of this activity was we had Surima code in non-Spark, and we just wanted to parallelize it. But I have not compared other models, and I'm sure I'm sure a true ML model would probably do better, but once again, I would have to have that information of the future period to forecast out, or I have to think of a clever way to forecast the features out in a certain way to have accurate predictions. But yeah, so I have not compared the results. And my email, I will type that out here, and I guess you have my email now. Yeah, cool.
Sweet. Thank you so much, Rahul. That was great. That was really cool to see a demo. And thank you for answering everyone's questions. Everyone, I know we can't hear anyone clap, but please give it up for Rahul and Adrian. Please reach out an email or LinkedIn and tell them how much you appreciated them. Again, I'd love to give another shout out to Taylor and Carolyn, who helped set this up, Rahul, Adrian, who spoke, and everyone else who was in it today listening, and hopefully you learned something new. As a question came up in the Q&A, we have recorded this and we'll be sending out to everybody shortly after this. Yeah, and I hope you have a great rest of your Wednesday evening or Wednesday, whatever time it is, wherever you are. Yeah, and again, thank you so much for stopping by to spend time talking about data science with us.